Differential equations in the real world, which I guess is a fancy way of saying practical questions. What do we got? A tank has got 30 litres of a solution of a chemical in the water. The concentration of the chemical is reduced by running pure water into the tank at a rate of 1 litre per minute and allowing the solution to run out of the tank at 2 litres per minute. The tank at any time has X litres time T. Okay, so the first part is to show that dx to t is minus 2x on 30 minus t. So some sort of explanation where this comes from. So I said, well, look, what do we know? We know every minute the volume of the tank is going down by 1 litre because we're pouring 1 litre in, 2 litres are coming out. Thus, in t minutes, the volume will end up being 30 minus t. That's where the 30 minus t comes from. Now, at time t, the fraction of the solution that is chemical then will be x out of the 30 minus t. Because we said, where it is, there it is, the tank contains x litres at time t. So we now know the fraction of the solution, that proportion, is x on 30 minus t. But it's escaping at 2 litres per minute, so therefore the amount that's flowing out will be twice that, because that's the fraction of 1 litre. So dx to t, it's going out at a rate of minus 2x on 30 minus t. Find the fraction of the original chemical still in the tank after 20 minutes. Well, I'm going to say the original volume is V. Now we know dx to t is minus 2x on 30 minus t. Separate my variables. Dx on 2x is minus the t on 30 minus t. So what this is going to do is I'm going to come up with an equation that links x and t together, and then I'm going to sub into that equation. So we integrate both sides. On the left-hand side, we get a half a log x. Right-hand side, also a log 30 minus t. Sub in, I've moved the t to the right-hand side there, so I've got 2 log. But the left-hand side will get x over v. Right-hand side, 30 minus t over 30. So x over v, bringing the 2 into the log, that will become 30 minus t squared, and 30 squared, of course, is 900. Multiply by v, we have our formula for x. Sub in t equals 20, and we get v over 9, so the fraction is 1/9. Ooh, foxes. A population of foxes on an island modelled by, there's our logistic equation that we saw yesterday. Dy to t is y outside of 1 minus y. So y is the fraction of the island's carrying capacity after t years. Time t equals 0, population of foxes is estimated to be 1/4 of the carrying capacity. Using the substitution, y equals 1 on 1 minus w, transform the logistic equation to simply that. So we're going to simplify this equation down. Okay. So y is 1 on 1 minus w. So dy dt, well, I can't differentiate it with respect to t, but I can with respect to w. And if I do that, I'll get 1 on 1 minus w squared, but then I have to multiply by the w dt. Now remember, we know dy dt is y 1 minus y. So I can now say these two things must equal each other. So on the left-hand side, I've replaced dy dt with 1 on 1 minus w squared. The w dt is equal, and on the right-hand side, I've substituted in for y, so 1 over 1 minus w, etc. So we've got everything in terms of w now. So multiply by the 1 minus w squared, and we get the w dt is minus w. Why do that? Because look at what we've ended up with. It's the basic growth and decay question now. So the w dt is minus w. Find the solution. Okay, remember we know t equals 0, y equals 1/4. They were the initial conditions given to us. Well, I want to know what w is then, because I'm now playing with w. So substituting in, we get w is negative 3. Okay, back to our other part. We now know the w dt is minus w. That's our standard exponential growth and decay question. We will end up with minus 3 e to the minus t. Okay, so a e to the kt. K in this case is negative 1. And A represents the initial population, which we've just worked out is -3. So y is equal to 1 on 1 plus 3e to the minus t. Because remember, y is defined as 1 on 1 minus w. So we end up with 1 on 1 minus 3e to the -t. And we've got our equation. So how long will it take for the fox population to reach 3/4 of the island's carrying capacity? So 3/4 has to equal that. That's just an exponential equation to solve. So there we go. Log 9, so 2.19, around about 2.2 years. 2.2 years. And for the last example, something which is very appropriate for you all. A rumour is spreading amongst 1,000 students. Okay, we've actually got 1,200, but it makes the numbers nicer. 1,000 students in a school at a rate proportional to those that have heard it. See, so more people have heard it. And those who have not heard it. Ooh. So as time progresses, people care less about the rumour, i.e. the proportion rate doesn't end up being constant. So the rumour spreads according to this model. Dx to t is some constant, x, 1,000 minus x, over t plus 1. Now, if initially one student starts spreading the rumour, and that is of course how rumours start, as you would know, and after 1 hour, now 50 students have heard the rumour. Maybe it was mentioned down in the senior study room or something like that, and then out it goes. How many students have now heard the rumour after 3 hours? Okay, there's our equation. Let's integrate. So separate the variables. When t was equal to 0, it was just one person knew the rumour, the person that made it up. And we also know after an hour, 50 have. We should be able to get it from here. Left-hand side, what have I done there? Oh yes, partial fractions. So partial fractions, we end up with 1 on 1,000, 1 on x plus 1 on 1,000 minus x. Right-hand side, well that's just a log function. So we get k lots of log 1 plus t. Okay, I've moved the 1,000 to the right-hand side, so multiplied by 1,000. And I've done my integration. Subbing into that, so sub 50 in, then sub 1 in, and over on the right hand side we get 1,000 k's log 2. We've now worked out our constant. It's this wonderful expression, the log of 999 over 19 all over 1,000 log 2. We now want to know what happens after 3 hours. I'm using the same initial conditions, but this time, amazingly, it's the same integration as before, just different numbers now. Hang on, what's going on there? Well, what's going on there is, look, I really just can't be bothered working this out right now. But geez, I know it's going to be a constant number. So, and I'll work out what that constant number is later. So I'm just saying, it's equal to something, some constant. Left-hand side, if I substitute in the x and substitute in the 1, use my log laws, pull it all together, I get the log of 999x over 1,000 minus x. Okay, let's work out that constant. The constant will be, remember, this is the constant. 1,000 times k, that expression there, times the log of 4. Sub in 3, 3 plus 1 is 4. Sub in 0, you get 1. So log of 4 minus log of 1 is log of 4. Playing around with all that, we get 2 log 999 over 19. Again, I'm not going to write that down, I'll just leave it as c. So undoing the log, we get 999x on 1,000 minus x is e to the power of c. And there we have it. X is 1,000 e to the c over 999 plus e to the c. Now we can go to our calculator, 734.558. So around about 734 students have now heard the rumour after 3 hours. You see what happens when you start a rumour. 13E, we'll play around with some of those.